All right, welcome to The Explainer. Today we're going to talk about something that is truly one of the cornerstones of machine learning, linear regression. Now, I know, it might sound a little basic, but you're going to be amazed at how this powerful little algorithm can find incredible patterns hiding in plain sight. Let's dive in.
I know what you might be thinking. Can a simple straight line really predict the future? It sounds a bit like science fiction, doesn't it? Well, stick with me here, because the answer is actually a lot closer to yes than you might think, all thanks to the algorithm we're about to break down.
So let's start with something we all just kind of get. Imagine you have to predict a student's score on a big exam. What's the first question you'd ask them? For me, it's how many hours did you study? It's just common sense, right? The more time you put in, the better you're likely to do. This simple, intuitive idea is the perfect place for us to start.
And that simple idea is really the heart of our official definition. Linear regression is a type of supervised machine learning. All that means is that we train it on data where we already know the correct answers. And its entire mission in life, its one job, is to find the single best straight line that shows the relationship between an input, like our hours studied, and an output, like the exam score.
Okay, so if you've got this big cloud of data points on a graph, how does the machine possibly find that one perfect line out of an infinite number of options? Well, that's the whole game right there, and it's called finding the best fit line.
And to do that, we have to dust off an old friend from math class. Yep, it's y equals mx plus b. But don't worry, this isn't just some abstract formula. For us, this is literally the blueprint for our prediction machine. Let's take a quick look at what each piece does.
First, we've got y. That's the easy one. It's our goal, it's the thing we're trying to predict. In our little story, y is the student's final exam score. We call it the dependent variable because its value depends on the other stuff.
So then you have x. That's our input, the independent variable. It's the piece of data we're feeding into the model to help it make a prediction. For our student, x is just the number of hours they hit the books.
Now, m is the slope, and this is where things get interesting. The slope is the engine of our model. It tells us how much y changes every time x increases by 1. So if m equals, say, 5, our model believes that for every single extra hour of studying, a student's score will go up by 5 points.
And finally, there's b, the intercept. Just think of this as the starting point. It's the value the model would predict if x was 0. So what score would we expect from a student who studied for exactly 0 hours? That's our b.
So here's the key. The best line isn't just any old line. It's the one line that makes the total amount of error as small as possible. You can picture the error as the vertical distance from each of our real data points to the line we drew. The best fit line is the one that makes the sum of all those distances teeny tiny.
Right, minimize the error. Sounds good. But how does the machine actually do that? How does it learn the perfect values for m and b? This, my friends, is where the magic happens.
To learn, the machine needs a report card. It needs a way to grade itself. This is called a cost function. You could think of it as a total badness score. For any line it tries to draw, it calculates how far off it is for every single data point, squares those errors to punish bigger mistakes more harshly, and then averages them all out. A high score is bad, a low score is good. The goal is simple: get the lowest score possible.
And the process it uses to get that score down is called gradient descent. The best way to picture it is to imagine a giant foggy valley. The lowest point at the bottom of the valley is the perfect answer we're looking for. The algorithm starts by just taking a wild guess. It drops a ball somewhere on the side of the hill. Then it feels around and asks, okay, which way is downhill from here, and takes a little step. Then it does it again, and again, and again, taking tiny steps downhill over and over until it finally rolls to a stop at the very bottom where it can't go any lower. That spot, that's our best fit line.
Okay, so we've totally nailed the basics for when we have just one input variable. But let's be honest, the real world is way messier than that. Most problems depend on more than just one thing.
And that brings us to the difference between simple and multiple linear regression. Everything we've talked about so far, one input predicting one output, that's simple linear regression. But the real power comes from multiple linear regression, which lets you use the same idea with lots of inputs. Think about trying to predict a house price. You wouldn't just use its size, would you? Of course not. You'd want to include its location, its age, the number of bedrooms, the whole shebang. That's multiple regression.
So, this is all cool theory, but why does it really matter? Let's talk about where this algorithm is actually being used every single day to make huge decisions out there in the real world.
For something so straightforward, linear regression is an absolute superstar in data science. And there are a few big reasons why. First, it's blazing fast to run. Second, it's super easy to understand and explain to someone, which is a huge plus. And finally, its core ideas are the foundation for tons of more advanced models. So it's almost always the first thing you try as a baseline.
And its applications are, well, they're everywhere. In real estate, it's used to predict property prices. In finance, it's used to forecast economic trends. In e-commerce, it analyzes how a price change might impact sales. Even in farming, it's used to estimate crop yields based on things like rainfall and soil quality. It's incredibly versatile.
Now, it's not a magic wand. For linear regression to work properly, your data has to play by a few rules. The number one rule is right there in the name, linearity. The relationship you're modeling has to actually look like a straight line. If it's a big curve, this is the wrong tool for the job. Another big one is this monster word, no multicollinearity. All that means is that your input shouldn't be telling you the same thing twice. For example, you wouldn't try to predict someone's weight using their height in feet and their height in inches. It's redundant. You have to check these things to make sure your model is giving you a reliable answer.
So, let's sum it all up. The pros? Linear regression is fantastic. It's simple, it's fast, and it's easy to interpret. The cons? Well, its biggest strength is also its biggest weakness. It assumes the world works in straight lines. It can be totally thrown off by a few really weird data points or outliers, and it might just be too simple for really complex, messy problems.
And that leaves us with one final thought to chew on. We've seen just how powerful a simple straight line can be for making sense of the world, and even predicting what might happen next. But if this is what a simple line can do, it just begs the question, what other, more complex, curved, and intricate patterns are still out there, hiding in the data, just waiting for us to find the right tools to uncover them?